1st of July, NASA detected a mysterious object speeding toward Earth, and some actual bona fide experts think it might not be your typical space rock or maybe any kind of rock or a natural phenomenon at all.
What if an interstellar object whirling through our solar system is actually a nuclear-powered spacecraft sent by aliens to test how humans respond?
The interstellar origin and official designation. Atlas was first spotted on July 1, 2025, by the NASA-funded Asteroid Terrestrial Impact Last Alert System in Chile. Follow-up orbit solutions placed it on a clearly hyperbolic path, meaning it is not gravitationally bound to the Sun and therefore arrived from beyond the solar system. It is only the third confirmed interstellar visitor after Oumuamua and 2I Borisov, which is why baseline expectations are weak and caution is high. Shortly after discovery, signs of a developing coma led to a parallel comet designation, C/2025 N1 Atlas, while the interstellar status received the official 3I tag. This dual naming encodes both what it is doing now, behaving like a comet, and what it is, an object from interstellar space. That combination alone is rare enough to justify intensive scrutiny. Early imaging and photometry also indicated an exceptionally high approach speed of roughly 210,000 kilometers per hour, consistent with a long interstellar voyage. Such speed reduces observation windows and amplifies uncertainties in physical modeling, which is part of why teams escalated rapid multi-telescope campaigns. The brightness anomaly and size ambiguity. Hubble imaging places tight bounds on the nucleus size, while revealing atypical brightness behavior for an interstellar visitor. From Hubble data obtained in late July 2025, NASA reports an upper limit diameter near 5.6 kilometers, with a plausible lower bound near 320 meters if the surface is unusually reflective. That wide range exists because the observed light is a combination of the solid body and a dust, complicating simple reflectivity-based size estimates. The same images show a sun-facing dust coma and a faint tail pushed away by radiation pressure, confirming genuine comet-like activity rather than a bare, inert object. The size probability tension is one reason some researchers flagged 3I Atlas as anomalous. If the object were truly multi-kilometer in scale, the implied number of such large interstellar bodies would exceed reasonable mass budgets for ejected planetesimals, a point raised in early theoretical notes that use the brightness to argue against a very large, inert nucleus. This has prompted alternative interpretations, including unusually high reflectivity, dust-driven brightening that overestimates size, or more controversially, some form of self-illumination. The self-illumination idea remains speculative but has been explicitly argued by Avi Loeb, who points to the steep surface brightness profile and morphology in Hubble frames as being consistent with an active light source rather than reflected sunlight alone. This hypothesis would shrink the true body to the low end of the size range and resolve the mass budget problem, but it requires energy generation mechanisms that have not been demonstrated for natural comets. Mainstream teams emphasize that standard comet physics plus observational geometry can reproduce the brightness without invoking artificial light, and ongoing Hubble and James Webb campaigns are designed to test which explanation fits the data best. The trajectory and planetary encounters. Atlas is not just on any random hyperbolic track. Orbital solutions show it is moving in a retrograde orbit, tilted only about 5 degrees from the ecliptic plane, the flat plane where most planets orbit the Sunday. The odds of such a shallow inclination occurring purely by chance are small, estimated near 0.2% in early probability models. What raises further concern is the series of planetary flybys built into its path. On October 3, 2025, the object will pass within about 29 million kilometers of Mars. By October 29th, it will reach perihelion at 1.35 astronomical units from the Sunday. Later, it is projected to swing within 33 million kilometers of Jupiter. The combined odds of a random interstellar object passing that close to 3 separate major planets are about 1 in 20,000. That unusual alignment has triggered speculation of intentional targeting. The most suspicious aspect is its timing relative to Earth. Atlas will reach its closest solar approach when Earth is hidden on the far side of the Sun. making the object effectively unobservable from Earth-based telescopes during its brightest and most dynamic phase. Avi Loeb has called this a potential reverse solar Oberth maneuver, where a spacecraft might use a hidden high-thrust burn to slow down and remain captured in the solar system. Whether coincidence or design, the geometry perfectly shields the object from scrutiny at a critical moment. The composition and chemistry anomalies. James Webb spectrograph data from early August 2025 show an unusually carbon dioxide-rich coma relative to water, placing 3I/Atlas among the most extreme comets ever measured in this respect. Multiple reports describe a carbon dioxide to water dominance that is atypical for solar system comets and consistent with formation in a colder, carbon dioxide ice line region of a distant protoplanetary disk. A newsroom summary places the carbon dioxide to water ratio near an order of magnitude higher than usual, on the order of about 8:1, reinforcing the view that the object condensed under chemistry, unlike common Jupiter family or Oort cloud comets. While that single-figure estimate will be refined with peer review, it captures why chemists flagged 3I/Atlas as an outlier. Hubble imaging confirms genuine activity rather than an inert body, showing a dust cocoon with a faint tail swept by radiation pressure. That morphology anchors a natural explanation for much of the brightness and supports the working classification as an interstellar comet. NASA's current synthesis notes that the nucleus could be as small as roughly 1,000 feet or as large as roughly 3.5 miles, depending on reflectivity and dust contribution, and that the object remains safely distant from Earth. Complementary infrared observations reported alongside early community notes point to water ice and silicate-rich dust mixed in the coma, the expected byproducts of solar heating of an icy nucleus now inside the frost line. These ingredients can be present even if the carbon dioxide signature dominates, and they are consistent with a long dormant surface waking as insolation rises. Taken together, a carbon dioxide heavy coma plus ordinary dust physics explains why 3I/Atlas can look chemically alien, yet dynamically comet-like. The chemistry implies formation far from a parent star or prolonged exposure to radiation that preserved carbon dioxide while suppressing water vapor, while the dust coma explains the observed glow without requiring exotic mechanisms. Continued Webb and ground-based spectroscopy are the critical tests for whether the extreme carbon dioxide fraction persists as the object warms toward perihelion. The solar conjunction blind spot, near its closest approach to the Sun in late October 2025, 3I/Atlas moves into solar conjunction positioned on the far side of the Sun from Earth, so ground and Earth orbit telescopes cannot safely point at it during the most active phase. Public observing guides note it will be too close to the Sun to see around perihelion, and will only reappear for Earth-based viewing in November and December, after it has already passed peak heating. This geometry creates a critical data gap exactly when gas and dust output, jet structure, and potential non-gravitational accelerations are most diagnostic. Because Mars is much closer to the line of travel at that time, orbiters there may obtain unique images or spectra while Earth cannot, but those assets are not guaranteed to be tasked or pointed, and their observing windows are short. If no Mars-side data are captured, models will have to interpolate across the conjunction gap, lowering confidence in size, spin, and outgassing inferences made from pre- and post-perihelion datasets. NASA emphasizes there is no impact threat. The comet remains at least roughly 1.8 astronomical units from Earth, so the fear among scientists is not danger, but the risk of missing the narrow, best evidence window to discriminate between ordinary comet physics and any truly anomalous behavior. The mainstream natural comet case. Teams analyzing astrometry and imagery conclude 3I/Atlas behaves like a comet. It is on a clearly hyperbolic path, shows a sun-facing coma with a faint dust envelope, and will pass the Sun at roughly 1.4 astronomical units, while remaining farther than 1.8 astronomical units from Earth. These observables match standard comet physics and imply no impact risk to our planet. Spectroscopy adds a second line of evidence. Early James Webb observations report a carbon dioxide-rich coma with detectable water ice and silicate dust. An unusual carbon dioxide to water balance can arise naturally from formation beyond a carbon dioxide ice line, or from surface crusts that vent carbon dioxide before water as heating increases, so a chemically odd coma does not by itself require exotic explanations. Image morphology from Hubble teardrop-shaped dust, flowing away from an icy nucleus warmed by sunlight, fits standard outgassing scenarios that can also drive small non-gravitational accelerations. This is the same mechanism long used to explain subtle trajectory deviations in comets without invoking engines or self-illumination. Independent critiques have also addressed the self-luminous claim. Astronomers point out that steep surface brightness profiles can result from dust, physics, point spread function treatment, and inner coma modeling choices. Taken together with a clearly detected coma, there is no compelling need to posit an internal light source. The mainstream working hypothesis therefore remains that 3I, Atlas, is a natural interstellar comet until data demand otherwise. The non-gravitational acceleration tests. Astrometric teams fit 3I, Atlas's trajectory with standard comet models that include tiny, rocket-like pushes from outgassing in addition to gravity. In practice, they solve for 3 small acceleration components: radial, transverse, and normal, whose magnitudes and directions reveal whether escaping carbon dioxide or water vapor can explain any deviation from a purely gravitational path. With 3I, Atlas already showing a coma, the mainstream expectation is that any measured non-gravitational term should align away from the Sun and be consistent with ordinary outgassing near its perihelion at about 1.4 astronomical units in late October 2025. If those terms are absent, misaligned, or too large for the observed gas production, that would be a genuine red flag. Independent commentators have proposed using these fits as the cleanest discriminator between a natural comet and something exotic. For example, Avi Loeb outlined testable acceleration ranges and directions that, if confirmed, would be hard to reconcile with dust-gas physics. By contrast, NASA's current summaries emphasize that the working model remains a natural comet and that the object poses no hazard to Earth, so any departure from comet-like non-gravitational behavior would need to clear a high evidential bar. The artificial illumination claim and the mainstream rebuttal. Avi Loeb argues that the Hubble surface brightness profile of 3I/Atlas is so steep that reflected sunlight alone cannot explain it, proposing a self-luminous source that would make the true body far smaller than naive brightness-based size estimates. Counter-analyses from other astronomers point out that steep inner coma profiles can arise from ordinary dust physics, image processing, and model choices. They find no need to invoke an internal light source. Independent imaging from Hubble and ESA. Hubble shows a textbook, teardrop-shaped dust coma with the first hints of a tail, which is exactly what an active comet should look like. This morphology, plus the clearly hyperbolic track, underpins the current consensus that 3I/Atlas is a natural interstellar comet pending contrary evidence. The close planetary flybys and their significance. One of the most unsettling aspects of 3ATLAS is how precisely its path threads the inner solar system. After its July discovery, orbital projections were refined to show 3 significant encounters in rapid succession. On October 3rd, it will sweep within about 29 million kilometers of Mars. Just 26 days later, on October 29th, it will pass perihelion at 1.35 astronomical units from the Sunday. Finally, in December, it will cross near Jupiter at a closest approach of roughly 33 million kilometers. Each of these distances is non-threatening on human scales. Yet on dynamical grounds, the odds of one interstellar visitor hitting all 3 targets so closely in a single fly-through are vanishingly low, estimated at about 1 in 20,000. These encounters matter because gravitational tugs from Mars and Jupiter in particular can alter the outbound path. If Atlas is an ordinary comet, its exit trajectory should be calculable from these encounters, plus standard outgassing. But if deviations appear that cannot be reconciled, scientists will have to consider alternatives, either exotic natural processes like unusual jetting behavior, or something more speculative, such as active maneuvering. The Mars flyby offers a unique chance for direct imaging by the High-Resolution Imaging Science Experiment, HiRISE, aboard the Mars Reconnaissance Orbiter. A proposal circulated in August suggested retargeting HiRISE to capture sub-kilometer details of the nucleus or coma structure during the October approach. If approved, these would be the highest resolution images ever obtained of an interstellar object, surpassing even the distant Hubble and Webb data. The perihelion blind spot and the Oberth maneuver hypothesis. At its closest solar approach in late October, Atlas becomes unobservable from Earth due to conjunction. From our vantage, it disappears into solar glare during the most critical days of its orbit. This is not unusual for comets, but in this case, it has raised fears because it coincides exactly with the phase where non-gravitational forces, or even high-thrust burns if it were an engineered craft, would be most visible. Avi Loeb described this as a potential reverse Oberth maneuver. In astronautics, an Oberth maneuver uses a planetary gravity well plus thrust to increase speed. A reverse Oberth would instead break an object, allowing it to remain captured. If such a burn occurred while hidden behind the sun, Earth-based observers would miss it entirely. Skeptics counter that the geometry is simply coincidental, given thousands of random orientations are possible for interstellar objects. Yet the timing compounds the anomaly of its shallow 5-degree inclination and multiple close planetary encounters. Statistically, each layer of improbability forces scientists to ask whether they are dealing with an extraordinary coincidence or something requiring an entirely different category of explanation. The power requirement problem. If Atlas were self-luminous, as some have speculated, the energy demands would be extraordinary. Calculations suggest an output near 10 gigawatts, comparable to several large terrestrial power plants, sustained not just for days, but potentially over millions of years of interstellar travel. A natural nuclear source would require impossible concentrations of unstable isotopes. A thermal reservoir would radiate away in deep space long before arrival. Only some form of exotic physics or engineered reactor could plausibly provide such power. This energy budget paradox is a core reason mainstream astronomers prefer dust and reflectivity explanations. Without clear evidence of power generation, the natural model remains overwhelmingly more credible. The chemical fingerprints and interstellar provenance. Spectroscopic studies from Gemini South, NASA's Infrared Telescope Facility, and JWST have all converged on the same baseline. 3I/Atlas is releasing volatile ices dominated by carbon dioxide, mixed with water vapor, silicate dust, and carbonaceous material. What makes this significant is the isotopic purity of the water. Analyses suggest the water lacks the heavy isotope enrichments typically seen in solar system comets. This implies the ice condensed in a completely different stellar nursery, billions of years ago, offering a direct sample of chemistry from another star system. From a natural perspective, this is a breakthrough. By measuring isotope ratios and mineral inclusions, planetary scientists can test models of planet formation across the galaxy. But for those considering non-natural explanations, the composition also leaves room for intrigue. Advocates of the probe hypothesis note that a craft traveling interstellar distances could accumulate such a debris mantle over time. In that view, the observed ice and dust may be camouflage material accreted during millions of years of travel rather than primordial construction. Statistical improbabilities and fear of deliberate design. A hyperbolic comet entering the solar system is not shocking by itself. We expected to eventually detect many. But 3I/Atlas stacks improbability upon improbability. A retrograde orbit tilted only 5 degrees from the ecliptic. Close approaches to Mars and Jupiter, a perihelion hidden behind the Sun, and a brightness curve unlike any standard comet. Each factor can be explained away individually as chance. Taken together, the statistical weight makes some astronomers uneasy. Loeb and collaborators calculated the odds of such alignments occurring randomly as less than 1 in 20,000. That level of coincidence, while not impossible, pushes into territory where scientists begin to ask whether random chance is still the best null hypothesis. The alien of the gaps caution. Mainstream astrophysicists caution strongly against defaulting to technological explanations for gaps in our knowledge. Neil deGrasse Tyson has argued that throughout history, when humans faced unexplained phenomena, they invoked gods or myths, the so-called God of the Gaps. Today, in the absence of clear evidence, that role is often replaced by aliens, Tyson stresses that while alien probes are not impossible, leaping to that conclusion without data undermines the scientific process. In his view, 3I, Atlas is better treated as a new kind of interstellar comet, whose anomalies expand our models rather than overturn them. Lessons from earlier interstellar visitors. The scientific unease around 3I/Atlas does not emerge in a vacuum. The two earlier interstellar visitors, 1I/Oumuamua in 2017 and 2I/Borisov in 2019, already showed that these bodies can defy expectations. Oumuamua displayed a cigar or pancake-like shape, rapid tumbling, and a small non-gravitational acceleration without a detectable coma. This combination led Avi Loeb to suggest artificial origins. Though most astronomers prefer exotic but natural explanations, such as hydrogen ice sublimation or ultraporous fractal dust, Borisov, by contrast, behaved much more like a normal comet, with clear gas and dust emissions, and its chemistry matched outer solar system comets. Placed in that context, Atlas sits uneasily between the two. It shows a visible coma and tail like Borisov, yet its carbon dioxide heavy chemistry and steep brightness profile echo the strangeness of Oumuamua. This hybrid behavior forces scientists to admit that our current taxonomy of comets and asteroids may not capture the true diversity of interstellar debris. Some anomalies may be natural, but outside the range we have studied. Others might be new categories altogether. The energy supply paradox revisited. Calculations of what would be required if Atlas were producing its own light emphasize how extraordinary such a claim would be. 10 gigawatts of continuous output is comparable to the total electrical demand of a mid-sized nation. No known natural body can sustain that in interstellar space without rapidly exhausting fuel. Radioactive decay is limited by isotope abundance, and any primordial heating should have dissipated over billions of years. For artificial explanations, sustaining such output over a million-year voyage implies advanced technology orders of magnitude beyond human capacity. Mainstream astronomers therefore treat self-illumination as a last resort hypothesis, one that demands extraordinary proof. The upcoming observational tests, the months ahead, determine whether Atlas becomes a resolved mystery or deepens into a cosmic enigma. James Webb Space Telescope is already monitoring its infrared output. Increases in water vapor and carbon monoxide as it nears perihelion would strongly confirm an active comet. The Mars Reconnaissance Orbiter's HiRISE camera may capture images during the October 3rd flyby, offering unprecedented close-up data from another planet's vantage. By December, as Earth regains visibility, ground-based observatories, and the new Vera-C, Rubin Observatory will resume tracking. Rubin in particular promises statistical context. If dozens of such objects are found each year, then the odds of encountering strange ones increase, potentially normalizing Atlas's behavior. If, however, Atlas remains an outlier among dozens, then the suspicions of something extraordinary will persist. The Vera-C Rubin Observatory and the dawn of interstellar population studies. The Rubin Observatory, formerly LSST, began early operations in 2025. It is designed to scan the entire visible sky every few nights, detecting faint moving objects down to much smaller sizes than Hubble or ground-based surveys could systematically catalog before. For interstellar research, this is transformative. Instead of waiting decades for a chance encounter, astronomers now expect to find dozens of interstellar comets and asteroids per year. That statistical baseline is crucial. If 3I/Atlas is representative, then many incoming bodies should show steep brightness profiles, unusual carbon dioxide chemistry, and shallow inclinations. If none of the future objects share these traits, then Atlas will stand out as a singular anomaly. What scientists actually fear. The fear is not that Atlas will collide with Earth. Its closest approach is nearly 2 astronomical units away, well beyond Mars's orbit. Nor is it simply fear of aliens. The real scientific fear is missing the chance to resolve its mysteries. The solar conjunction blind spot means the best opportunity to catch anomalous activity could slip by unobserved. A second fear is epistemic. If Atlas's properties defy natural explanations, yet no consensus forms, astronomy risks a rift between speculative and conservative camps, much like the ongoing debates over Oumuamua. Finally, there is the existential fear, however small the probability, that Atlas is not a rock at all, but technology from elsewhere. A finding that would upend humanity's place in the universe. Even cautious scientists acknowledge that possibility must remain on the list, if only at the very bottom. The December Earth-side return of visibility. After disappearing behind the Sun at perihelion, Atlas reemerges in December 2025. At that point, it will be faintly visible to powerful ground telescopes in the northern hemisphere. This phase will allow astronomers to measure post-perihelion outgassing, track any trajectory changes induced during the hidden interval, and compare them to pre-perihelion models. If the trajectory shows only small deviations consistent with cometary jets, the case for a natural object will strengthen. But if unexplained accelerations or sudden dimming or brightening occurred while unobservable, those anomalies will carry even greater weight, since they happened under the cover of solar glare. The official stance and safe geometry. NASA's current overview states that 3I/Atlas is unequivocally interstellar, on a hyperbolic path, and poses no impact threat to Earth. Its closest approach to our planet is about 1.8 astronomical units farther than Mars's average orbital distance, while perihelion occurs near 1.4 astronomical units around late October 2025. The page notes ground observers will lose sight during solar conjunction and regain visibility in early December, setting clear windows for before and after comparisons. What Hubble's morphology really shows. Hubble's July 21st imaging resolves a teardrop-shaped dust cocoon with a sunward plume and the first hint of a radiation pressure tail, all classic signatures of an active icy nucleus. From those data, NASA reports a nucleus diameter no larger than about 5.6 kilometers and possibly as small as about 320 meters, because the unresolved solid body is embedded in dust that boosts apparent brightness. A morphology consistent with dust outflow directly supports natural comet physics and provides a quantitative dust loss rate comparable to comets first detected hundreds of millions of kilometers from the Sun. Independent write-ups of the same Hubble frames reiterate those constraints and add two practical points for observers. First, 3I/Atlas was discovered at roughly 675 million kilometers from the Sun, well beyond the water ice activity line, so early activity likely reflects more volatile species than water. Second, the object will drop into solar glare through September and reappear in early December, bracketing the critical period when dust production may peak. Webb's first chemical readout and why the ratios matter. Early James Webb spectroscopy detects carbon dioxide, water ice, carbon monoxide, and carbonyl sulfide in the coma, but with an unusually high carbon dioxide to water ratio reported as the highest yet measured for a comet. Two natural explanations fit these data. The nucleus could be intrinsically carbon dioxide rich from birth, having formed beyond a carbon dioxide ice line in a very cold protoplanetary disk, or the surface could possess an insulating crust that vents carbon dioxide more readily than water at the current heliocentric distance. Either path implies formation conditions unlike most cataloged solar system comets. Follow-on coverage emphasizes the same conclusion from a broader context. Interstellar comets sample chemistry from other stellar nurseries. So extreme carbon dioxide dominance is evidence of provenance, not necessarily of anomaly. As the object warms toward perihelion, the community expects water outgassing to rise. Whether the carbon dioxide dominance persists or converges toward typical water-rich behavior is a decisive near-term test. The self-illumination claim versus the image physics rebuttal. Avi Loeb has argued that the inner surface brightness slope in the Hubble image is too steep for reflected sunlight alone, and is best explained by an internal light source, which would also shrink the implied nucleus size and sidestep population statistics problems. Multiple astronomers have published technical rebuttals showing that steep inner coma profiles can naturally emerge from dust production physics, image processing choices, and how a point spread function is handled near the unresolved nucleus. They further note that Hubble's own morphology, sunward coma with a nascent tail, already matches a textbook active comet, removing the need to invoke an emitting device. These critiques, together with NASA's size limit analysis, form the mainstream position that 3I/Atlas is behaving like an interstellar comet until contrary evidence survives quantitative tests, the Mars-side opportunity and what it can and cannot resolve. orbital solutions show a close pass by Mars in early October 2025 at roughly 29 million kilometers, enabling a brief window for spacecraft at Mars to attempt imaging or spectroscopy from a vantage Earth cannot match during conjunction. A community white paper outlines a campaign concept involving Mars Reconnaissance Orbiter's HiRISE imager, China's Tianwen-1, and the Emirates HOPE mission, arguing that even coarse pixel scales could constrain coma asymmetries, jet geometry, and non-gravitational acceleration directions during peak activity. Public commentary further notes that even if HiRISE achieved order tens of kilometers per pixel, the data could still falsify a self-illumination scenario by confirming a dust-scattering phase function consistent with sunlight, and by detecting time-variable jets aligned with solar heating rather than thrust-like vectors. The essential point is that Mars-side snapshots, if obtained, would directly probe the period Earth-based telescopes cannot observe, closing the most consequential data gap in the timeline. The role of non-gravitational forces in testing the probe hypothesis. Every active comet experiences a kind of natural propulsion. As sunlight heats volatile ices, jets of gas and entrained dust escape, pushing the nucleus like miniature thrusters. These so-called non-gravitational accelerations can be measured precisely by tracking deviations from the path gravity alone would dictate. In the case of one I/Oumuamua, a tiny but persistent acceleration was detected without any visible coma, which is what opened the door to speculation about hidden engines or exotic ices. 2 I/Borisov, by contrast, showed acceleration entirely consistent with visible outgassing. For 3 I/Atlas, this test is critical. Its active coma means scientists expect measurable non-gravitational forces. If the accelerations align radially away from the Sun and their magnitudes match the observed dust and gas flux, then the comet explanation is validated. If accelerations are missing, misaligned, or too strong for the measured gas production, then more exotic explanations gain weight. This is why teams are preparing to compare pre-perihelion and post-perihelion astrometry with extreme precision. Any unexplained delta V in the days it spends hidden behind the Sun would stand out in the December recovery arc. Energy requirements revisited through engineering analogies. The suggestion that Atlas is self-illuminating forces consideration of energy budgets on an engineering scale. 10 gigawatts is not an abstract number. It is roughly the output of 10 nuclear power stations, or the total electricity consumption of a small country. No known comet can sustain such luminosity over millions of years. If artificial, that would imply an object capable of storing or generating energy orders of magnitude beyond human spacecraft. For perspective, NASA's New Horizons probe generated less than 200 watts of electrical power from its radioisotope generator, 50 million times smaller. This comparison illustrates why most scientists dismiss self-illumination as implausible. It implies technology vastly beyond our current energy storage and generation capabilities. 28. What the December reacquisition can confirm. When Atlas reemerges from conjunction in December 2025, astronomers will immediately attempt high-precision astrometry and spectroscopy. Several outcomes are possible. If the comet's trajectory deviates only by the amount predicted from Mars and Jupiter gravity plus modeled outgassing, the natural explanation stands. If water vapor flux rises as expected, the carbon dioxide dominance may shift, strengthening the cometary case. If its brightness profile shifts in unexpected ways, or if astrometry shows a sudden unexplained delta V, then hypotheses of unusual physics or even artificial maneuvering resurface. If Earth-based tracking is hampered by faintness or weather, a critical window could again be lost, leaving debate unresolved. This reacquisition phase is therefore viewed as the make-or-break test. Until then, scientists remain in a holding pattern, stacking probabilities, collecting indirect evidence, and preparing for decisive measurements once the object clears the Sunday, the shallow ecliptic tilt, and why geometry alone worries dynamicists. The inbound path is retrograde yet tilted only about 5 degrees from the ecliptic, the plane where the planets orbit. That alignment threads the inner solar system and naturally increases the chance of multiple planet flybys during a single passage. In the discovery window, Orbit fits pointed to a close pass by Mars in early October and another by Jupiter months later. Some solutions also include a modestly close pass by Venus, while Earth remains safely distant. Probability arguments assembled around this geometry claim that getting such a shallow tilt together with multiple close non-Earth encounters is rare. With one estimate placing the combined odds near 1 in 20,000, those figures are why some researchers flagged intent as a hypothesis to test rather than assume. What Mars-side spacecraft have already shown is possible. HiRISE on Mars Reconnaissance Orbiter has imaged a fast comet during a close Mars flyby before, namely Comet Sighting Spring in 2014. From ranges of order 138,000 kilometers, HiRISE achieved image scales near 138 meters per pixel and constrained the nucleus to be smaller than roughly 2 kilometers. Those precedents establish that even coarse, few pixel detections during a rapid pass can still bound nucleus size and reveal coma asymmetries, which are exactly the diagnostics needed to test whether sunlight scattering dust explains the brightness of 3I/Atlas during the period Earth cannot observe. Why solar conjunction really does close the most critical window. Near perihelion, the object sits too close to the Sun on the sky for standard assets. Hubble enforces a sun avoidance zone of roughly 50 degrees and suffers frequent Earth occultations each orbit, while James Webb must keep its line of sight between roughly 85 and 135 degrees from the Sun to protect its sunshield. These hard-pointing limits create a guaranteed data gap right when outgassing, jet geometry, and any non-gravitational acceleration should peak, so decisive tests of exotic claims depend on pre- and post-conjunction comparisons, or on opportunistic imaging from spacecraft at Mars, how non-gravitational accelerations are measured, and why they matter here. Astrometrists solve for 3 tiny acceleration components, radial, transverse, and normal, using the Marsden formalism, which ties each component to a distance-dependent sublimation law that approximates how a venting comet behaves as it warms and cools. When the fitted components point away from the Sun in scale, with the measured gas and dust flux, ordinary outgassing is sufficient. When components are missing, misaligned, or too large for the inferred production rates, something beyond standard comet physics must be invoked. For 3I/Atlas, the clean experiment is to compare fits derived from the pre-conjunction arc with those from the December recovery arc and ask whether the change in velocity across the hidden interval matches the outgassing one would expect from a carbon dioxide-rich activity. Concrete, falsifiable signatures that would settle the self-illumination claim. A self-luminous source must betray itself in at least 3 independent ways. First, the phase angle dependence of brightness should decouple from standard dust scattering laws. A persistent inner coma profile steeper than dust models allow, across changing geometries, would be a red flag. Second, spectra should reveal excess continuum or line emission not explainable by reflected sunlight plus thermal radiation. James Webb's wavelength coverage can verify this. Third, the non-gravitational acceleration should either be absent despite strong brightness or point in directions inconsistent with solar heating. If, instead, Hubble-class morphology continues to show a sunward coma with a radiation pressure tail, Mars-side snapshots reveal jet-like structures, and astrometry yields radial-dominant accelerations that scale with gas production, the illumination reduces to ordinary sunlight on dust, and the exotic hypothesis is falsified. Why some scientists still quantify low-probability intent despite a natural baseline. Advocates of technological hypotheses cite the shallow tilt, the sequence of non-Earth planetary passes, and the conjunction-timed perihelion, combining them into a statistical case that such alignments are improbable if every interstellar visitor is random. In their framing, the correct response is not to assume intent, but to enumerate clear observational tests, morphology, spectra, and acceleration vectors, and then check them. The mainstream response is to keep the null of a natural interstellar comet until those tests fail. Nonetheless, laying out the low-probability geometry and its implications is part of defining what would count as extraordinary evidence. The broader implications for planetary science. Even if 3I/Atlas proves to be fully natural, its chemistry and dynamics already expand the known range of cometary behavior. A carbon dioxide-dominant coma, isotopically pristine water ice, and activity detected well beyond the traditional frost line, all point to interstellar comet reservoirs having different structures than the Kuiper belt or Oort cloud. This helps test models of planetary system formation. Simulations that predict efficient ejection of carbon dioxide-rich planetesimals from outer disks now gain empirical support. ATLAS is therefore valuable, regardless of whether it confirms or refutes exotic hypotheses. The communication gap between science and the public. Part of the fear narrative arises because sensational interpretations, self-illumination, alien probes, deliberate targeting spread quickly through media channels, while the slower, technical rebuttals from comet dynamicists reach a smaller audience. This pattern was evident with Oumuamua as well. Mainstream astronomers emphasize incremental tests, probability models, and conservative null hypotheses, but public attention gravitates toward extraordinary claims. Scientists therefore worry not only about what ATLAS is, but about how debates over it are perceived, potentially fueling mistrust if anomalies are oversimplified or misrepresented. The ultimate stakes. What hangs over all these discussions is the possibility remote, but not zero, that 3I/Atlas is more than natural debris. If anomalous accelerations, unexplained light production, or improbably precise geometry survive all scrutiny, then humanity would confront its first evidence of extraterrestrial technology. That prospect drives both fascination and fear. Fascination, because it would answer a question asked for millennia. Are we alone? Fear, because the implications for human civilization, culture, and security would be immense. It is this razor's edge between ordinary comet and extraordinary probe that makes ATLAS the most closely watched interstellar visitor to date. Historical precedent. Fear versus discovery. Each time humanity has encountered a new category of cosmic body, fear has accompanied discovery. In the 17th century, comets were viewed as omens of disaster until telescopic observations proved their predictable orbits. In the 20th century, near-Earth asteroids triggered existential concern before planetary defense strategies were developed. Now, interstellar objects like Oumuamua, Borisov, and ATLAS represent the next chapter. Unfamiliar bodies whose properties stretch existing models. The fear is partly scientific, worrying about what anomalies mean for our theories, and partly cultural, because history shows that unexplained phenomena quickly attract speculative, and sometimes destabilizing, interpretations. Why isotopes may hold the final answer. One of the most decisive tests lies in isotope ratios. Water and carbon in the solar system carry distinctive fingerprints, such as deuterium to hydrogen, D/H ratios. If ATLAS's ices carry isotope ratios starkly different from any measured in local comets, that alone confirms its interstellar origin beyond doubt. If those ratios fall within local ranges, it raises the question of whether material from other star systems is chemically less distinct than assumed. In either case, isotope data are less vulnerable to misinterpretation than brightness profiles or geometric coincidences, making them a high-priority target for Webb's infrared spectrographs. The December recovery as a turning point. By early December 2025, Earth regains line of sight. Large ground-based telescopes, Keck, VLT, Gemini North alongside the Vera C. Rubin Observatory will attempt coordinated tracking. The goals are threefold. Measure the trajectory to milli-arcsecond precision, capture spectral shifts as activity wanes, and resolve coma structure at higher signal-to-noise than before conjunction. This recovery period may either dissolve the mystery if data neatly fit cometary models, or sharpen it dramatically if unexplained delta V or brightness anomalies are confirmed. For scientists, this is the moment where years of speculation either converge to a mundane explanation or escalate towards something paradigm-shifting. The role of peer review and scientific caution. Mainstream researchers emphasize that extraordinary claims require extraordinary evidence. Peer-reviewed studies are intentionally slow, designed to check biases and filter out premature conclusions. While Avi Loeb and collaborators have pushed the artificial hypothesis frontier quickly into public discourse, others urge patience until perihelion and recovery data are fully analyzed. This tension between rapid speculation and cautious accumulation of evidence underlies much of the fear narrative. It is not fear of aliens per se, but fear that science's credibility could suffer if claims outpace data and collapse under scrutiny. What comes next beyond Atlas? Whether Atlas proves ordinary or extraordinary, it signals the start of a new era. With the Rubin Observatory set to detect dozens of interstellar visitors each year, scientists will soon have a statistical catalog large enough to separate anomalies from patterns. If most look like Borisov, Atlas will stand as an outlier to be explained. If many show Oumuamua-like or Atlas-like strangeness, then our concept of typical comet will need radical revision. In either outcome, interstellar objects will evolve from rare curiosities into a core research field, reshaping how we understand planetary system formation, galactic dynamics, and perhaps even extraterrestrial technology. Why interstellar debris challenges solar system models. Traditional solar system formation models suggest that during the chaotic birth of planets, billions of icy planetesimals were ejected into interstellar space. But those simulations also show most ejected bodies should be small, inert, and irregular. The discovery of multiple active interstellar comets within just 1 decade, Borisov and Atlas, suggests either we underestimated the efficiency of ejecting large, volatile-rich bodies, or something else is biasing which ones reach us. Atlas intensifies this puzzle by being both active and chemically extreme, implying either our models of early planetary system chemistry are incomplete, or that we are sampling a very peculiar reservoir of objects, fear of hidden forces and unexplained acceleration. The case of Oumuamua set a precedent. Its small but real acceleration could not be fully explained by standard cometary jets. Scientists fear a repeat with Atlas. If astrometry after conjunction reveals even tiny unexplained deviations, debate will erupt again about whether outgassing can account for them. Unlike Oumuamua, Atlas already shows a coma, so outgassing should explain acceleration. If it doesn't, then something genuinely new, physical, or artificial must be invoked. This anticipation of potential déjà vu fuels unease, because it suggests we still don't know how to interpret interstellar bodies, the Sun as a shield and stage. The fact that Atlas's perihelion is perfectly timed to be hidden behind the Sun adds a psychological layer to the fear. For natural comets, such geometry is coincidence. For those entertaining the probe hypothesis, the Sun acts like a cosmic curtain, shielding whatever might happen from human eyes. Even cautious scientists admit this timing is uncanny. The object brightens most and possibly changes course exactly when it cannot be observed. While the mainstream sees coincidence, the public sees concealment, and that perception gap itself is a source of anxiety. The limits of current technology. Even with Hubble, James Webb, and Rubin, humanity's observational capabilities are stretched thin when it comes to fast-moving, faint interstellar objects. Atlas's distance at perihelion, over 1 astronomical unit, means we cannot resolve its nucleus directly, only its dust envelope. No spacecraft is in position to intercept it, and none can be launched in time. This highlights a systemic fear among scientists. We are watching these cosmic visitors slip past with no way to capture definitive data. The frustration is that even if Atlas is extraordinary, our tools may not be sufficient to prove it. The needle in a haystack paradox. The galaxy should contain countless interstellar fragments, yet we've only detected 3 in modern times. If Atlas turns out to have both anomalous geometry and unusual chemistry, then either we are extraordinarily lucky catching rare outliers back-to-back, or something biases which kinds of interstellar bodies pass near Earth. That bias could be dynamical, chemical, or, in the most speculative interpretations, deliberate. The paradox is unsettling because it implies either we don't yet understand galactic traffic patterns, or we are seeing something much stranger than random debris. The challenge of international coordination, tracking and interpreting 3I, Atlas requires data from dozens of observatories worldwide, plus spacecraft assets at Mars. Scientists fear that gaps in coordination caused by limited telescope time, national priorities, or even bad weather could leave critical holes in the dataset. Unlike periodic comets that return, Atlas will never come back. Any lost observation window is permanent. This amplifies the pressure. One missed campaign could mean the difference between resolving anomalies or leaving them forever ambiguous. Fear of bias creeping into interpretations. In high-profile cases like Atlas, confirmation bias is a serious risk. Advocates of the artificial hypothesis may overemphasize statistical coincidences, while conservative astronomers may downplay real anomalies to avoid sensationalism. Scientists worry that their own community's biases, toward caution or toward speculation, could distort the interpretation of evidence. This fear is less about ATLAS itself, and more about protecting the integrity of the scientific process under public scrutiny. Implications for planetary defense. Even though ATLAS poses no direct threat, its closest approach is nearly 2 astronomical units from Earth. Its discovery highlights a planetary defense blind spot. If a truly hazardous interstellar object entered on a similar trajectory, we would have very little time to react, given its extreme speed and late detection. ATLAS therefore fuels fear not because it endangers Earth, but because it exposes how unprepared humanity still is for monitoring fast-moving extrasolar bodies. The existential fear of being observed. If, in the most speculative scenario, ATLAS is a probe, then it implies one thing above all: we are not alone, and we may already be under observation. For some scientists, even entertaining this possibility is unsettling. The asymmetry, where another civilization is advanced enough to send craft across interstellar space, while we can barely reach the edge of our solar system, underscores our vulnerability. This is perhaps the deepest fear. Not collision, not chemistry, but the possibility of surveillance. Fear of missing unique science forever. Unlike planets or periodic comets, 3I, ATLAS will only pass through the solar system once. After perihelion, it will leave forever into interstellar space. If observations are incomplete or data are inconclusive, the chance to study its chemistry, morphology, and dynamics is permanently lost. Scientists fear this once-and-gone reality more than anything else, because no future telescope or mission can revisit the object once it exits. Data overload versus interpretation. While there is a fear of missing data, there is also the opposite. Too much fragmented information. Observations are being taken by Hubble, James Webb, dozens of ground observatories, and possibly Mars orbiters. Each uses different instruments, wavelengths, and calibration methods. Integrating this into a coherent physical model is a massive task. Scientists fear that conflicting results, such as one spectrum suggesting high water and another showing dominance of carbon dioxide, will muddy the picture rather than clarify it, leaving ambiguity that may never be resolved. Fear of public misinterpretation. History shows that when anomalies appear in astronomy, the public often gravitates to extraordinary explanations. With ATLAS, claims of alien probes already circulate online. Scientists fear that if they fail to explain anomalies quickly, conspiracy theories and misinformation will fill the gap. This risks undermining public trust in astronomy and could distort funding and research priorities toward defending against aliens instead of studying the object with scientific neutrality. Fear of precedent for future objects. If ATLAS remains anomalous even after exhaustive study, it sets a precedent. Future interstellar comets will arrive with the expectation of extraordinary explanations. This means every unusual light curve or trajectory deviation could spark new cycles of speculation and media frenzy. Scientists fear being trapped in a pattern where each interstellar detection becomes less about learning natural science and more about defending against or debating sensational claims. The silence of the rest of the galaxy. A final, more philosophical fear lies beneath. If ATLAS is natural, it means interstellar debris is common, but civilizations are silent, reinforcing the paradox of why we see no clear signs of life despite billions of stars. If ATLAS is artificial, then we are faced with the reality that someone or something has already crossed interstellar space, while humanity has not. Both outcomes are unsettling. Either we are truly alone in a galaxy filled with lifeless debris, or we are the latecomers in a galaxy where others are already watching. Fear of anomalous communication signals. Though no credible radio emissions have been detected, some researchers have raised the possibility of using SETI arrays to listen to 3I ATLAS. The fear is that if even faint, structured radio signals were found, it would immediately elevate ATLAS from a cometary curiosity to evidence of an interstellar probe. The scientific community is not prepared for the social and political consequences of such a detection, which could spark global panic or misinformation before peer review even confirms the data. Fear of gravitational capture. Most interstellar visitors pass through the solar system once and then leave forever. But if Atlas performed a hidden braking maneuver or simply lost enough velocity through interactions with Mars and Jupiter, it could, in theory, be captured into a bound orbit around the Sun. The idea of an interstellar body deciding to stay rather than passing through has unnerved some commentators. While natural capture is exceedingly rare, even the faint possibility feeds speculation about deliberate maneuvering. Fear of technological asymmetry. If Atlas is artificial, then its builders are already centuries or millennia ahead of us technologically. The fear is not that they are hostile, but that the gulf in capability makes humanity irrelevant. We could be ants watching a drone fly overhead aware of its presence, but powerless to interpret its purpose or respond meaningfully. This existential asymmetry fuels unease among even those who privately entertain the probe hypothesis. Fear of misallocation of scientific effort. Atlas demands immense telescope time and computing resources, which are being diverted from other urgent astronomical projects. Some scientists fear that if Atlas proves to be ordinary after all, this intense diversion may be seen as wasteful, leading to backlash against future interstellar object campaigns. The irony is that fear of missing something extraordinary could end up weakening support for the very science that might one day confirm it. The paradox of visibility and invisibility. Perhaps the most unsettling aspect of Atlas is how much of its story unfolds outside our line of sight. At perihelion, it hides behind the Sunday. At closest Mars approach, only orbiters might glimpse it. By the time Earth regains visibility, it may already have altered course or expelled its most diagnostic gases. Scientists fear that the universe has presented them with a perfect mystery, but one that is structured so they cannot solve it. The object is visible enough to spark questions, but invisible at the very moments needed to answer them. Fear of discovering non-human artifacts. If Atlas is artificial, the most profound fear is that it could be a derelict technology abandoned or drifting for millennia. Discovering alien ruins rather than alien contact would answer the question of whether we are alone, but in the most unsettling way. Yes, others existed, but they are gone. Scientists fear this scenario because it implies civilizations can travel the stars and still vanish, leaving only fragments behind. Fear of failing to convince the public. Even if anomalies are detected, say, an unexplained acceleration or unusual emission spectra, scientists fear they may be unable to communicate the evidence convincingly to the wider world. The complexity of astrometric fits and coma physics is easily overshadowed by sensationalist narratives. If the truth is nuanced but the headlines are absolute, public belief could split between unquestioning hype and deep skepticism. With science caught in the middle, fear of triggering a false alarm. The flip side of under-communicating is over-communicating. If a research team prematurely announces evidence of artificial origin and later retracts, the backlash could damage the credibility of interstellar research for decades. This fear makes some scientists hesitant to even speculate openly, lest their caution be stripped away in headlines. Atlas is therefore as much a communications challenge as a scientific one. Fear of a shift in humanity's priorities. Some scientists privately worry that if Atlas were proven artificial, governments and militaries would seize control of the narrative. Research might be classified, telescopes restricted, and astronomy co-opted into defense projects. The fear here is not aliens, but humanity's own reaction, that an extraordinary discovery would fracture global cooperation rather than unite it. Fear of irrelevance in the cosmic scale. Finally, Atlas revives an old philosophical fear. If the universe can throw enormous icy fragments or even engineered objects across interstellar distances with ease, then humanity struggles to leave even its own solar system look small. The object is a reminder of how young and fragile our species is. Whether it is just a comet or something far stranger, Atlas underscores the gulf between our aspirations and the forces at play in the wider galaxy. Fear of unrecognized physics. If Atlas behaves in ways that cannot be reconciled with current comet models, the fear is that we may be glimpsing physics we don't yet understand, perhaps new mechanisms of outgassing, heat transfer, or radiation interaction. This fear isn't about aliens, but about gaps in fundamental knowledge. A failure to explain Atlas naturally would signal that even the most basic processes in planetary science may be incomplete. Fear of statistical illusions. Astronomers know that low-number statistics can be deceptive. With only 3 interstellar objects ever observed, it is difficult to distinguish true anomalies from statistical outliers. Scientists fear that if Atlas is simply weird by chance, we might overinterpret its significance, shaping entire theories around what is actually noise. The danger is not that Atlas is extraordinary, but that it misleads us into thinking it is. Fear of technological unreadiness. If Atlas were confirmed to be artificial, humanity would face a terrible irony. Proof of extraterrestrial technology without the capability to reach or intercept it. Even our fastest probes would take decades to catch up, by which time Atlas would be far out of range. This mismatch creates fear of helplessness, an opportunity that appears and vanishes before we can respond, leaving only distant data and unanswered questions. Fear of repeating history with future interstellar arrivals. Scientists already anticipate more interstellar objects will be found in the coming years, especially with the Vera C. Rubin Observatory. But there is fear that we will continue to watch them slip past, always unprepared to launch intercept missions in time. Atlas becomes a symbol of missed chances, reinforcing the dread that by the time humanity organizes itself to act, the truly extraordinary object will have come and gone.